we need to review a little bit of implicit differentiation. So up until this point in calculus, we've been using y prime to represent the derivative. We've also used this notation, dy dx. They both say find the first derivative, but this notation right here gives more information. This comes from what's the change of y over the change of x. So in other words, if something went from this point up to this point in a straight line, then we could figure out, well, it moved over in this direction by delta x, and it went up this much, delta y. And if you divide those two, delta y over delta x, you would find the slope. So this information is shorthand for all of this information. Now, if it was a situation, let's say that these measurements were in feet, then delta y would be something like 15 feet. And the horizontal distance, delta x, would be something like 5 feet. So notice in this case, feet and feet cancel out, and you're left with a slope of 3. So in other words, the slope of this line is 3. But y prime doesn't have to just be dy dx. It could, for example, be dy dt, which is saying, okay, this thing is going up, but it takes some time to do it. It can't just do it without time passing, so that's what this represents. So this could then say, okay, it traveled up 15 feet, and it took 7 seconds to do it. So now we have some information as it traveled at a height from here up to here, it took 7 seconds to do that. So then our answer would be in feet per second, which is a velocity. So the first derivative is telling us a velocity. It's 15/7 feet per second. Okay, so you have to pay attention to the variables. So in this case, it's the y and the t that are important. It's not always going to be just y and x. So here's an example that doesn't have just y and x. Find the change of w over the change of time, or dw dt, which if we did the shorthand notation, we would just call it w prime. But like I say, this gives more information because this is saying w is changing, so w could represent width. The width of something is changing over time. Here's the equation that represents the function. Since I need to take the derivative, I'm going to have to use the product rule. To begin with, take the derivative of the first function. So derivative of t squared is 2t. And then the chain rule says you need to also take the derivative of the inside of this function. Well, the inside of this function is the letter t. So we need to take the derivative of t, and then the denominator stays the same as the directions, dt. Then the product rule says leave w alone, and then go plus, this time leave t squared alone, and now take the derivative of w. Well, since we don't know exactly what w equals, we'll just say take the derivative of w with respect to time. And then on the right hand side, the derivative of a constant 5 is 0. Okay, now back to the question. It says when t equals 1. Well, if we're supposed to find dw dt, then we need a number for this t. dt over dt, that's easy, that's just 1. We need a number for this w, we need a number for this, and then we're going to solve for this. So what I prefer to do is plug the numbers in first. T is not, oh yes it is given, it's right there, t equals 1, good. So we'll put a 1 right there, a 1 right here, and then what do we put for w? Well, in this case what we're going to have to do is go over to this, what's called the main equation, plug in t equals 1, and then find out what W equals. So W equals 5. Okay, so we have W, we have this, and that's all the numbers we need. So it's going to be 2 times 1 times 1, and then W is a 5. And then T squared, so that's going to be 1 squared, times dW dt equals 0 still. The last thing to do is solve for dW dt. So this right here is a 10, so subtract 10 from both sides. This is just a 1, so it's going to say dW dt equals negative 10. So if this were a physical application, this would say something like the change of the width over time is negative 10. And then we would have some units right here like feet per second or something like that that would be given if it was a application problem. So this would say the width is changing over time at 10 feet per second. Because it's negative, that means the width is getting smaller. So in other words, this object is shrinking, its width is shrinking at 10 feet every second. Let's look at another example. So here's one where an object is moving. It goes around this purple ellipse right here. And before section 3.9, we would just look at this as a static object. There's just an ellipse there. But now that we have this idea that things can change over time, we can say, okay, this is a planet or something like that that's traveling around the ellipse. And as it goes around, so for example, if it goes from here to right here, then its y value has gotten bigger and its x value has gotten smaller. So we can talk about the change of y, that it went up, change of x, it went to the left. So that's what this means, dy dx. So we've got this equation. Take the derivative. The derivative of this is going to be 2x. And then you need to take the derivative of x, so that's going to be derivative of x with respect to whatever the denominator is, dx, leave that the same. And then this 9, because it's a constant, just stays there. Now do the same thing over here. It's going to be 2y, and then the chain rule says take the derivative of the y, so dy dx, and it's still over 16. On the right side, the derivative of 1 is 0. Okay, now I've basically got the same type of case as last time, which is typical. What you do is take the equation, take the derivative with respect to whatever's in the denominator, derivatives, plug in the given information, and then do the algebra to solve for whatever is being asked for. Which means that we need a number for this, a number for this, and a number for this. Well, this one's easy enough, dx over dx, that's just 1. And this one's easy enough, x equals 1. But what does y equal? So we have to do the same thing as last time, and that is take this given information, plug in the number that was given, x equals 1, so that would be 1 squared over 9 plus y squared over 16 equals 1. So you substitute the given information into the given function, find out what y equals. Basically, if you look at the picture, that's saying, okay, right here, x equals 1. And if x equals 1, what does y equal at that point? That's what we're doing over here. So let's see, this is 1/9, which we need to subtract from both sides. So the left side will stay the same. 1 minus 1/9 is 8/9. So y squared equals, I'm going to do it like this, 8 times 16 divided by 9, and then take the square root of both sides. So the square root of 8 is 2 radical 2. The square root of 16 is 4, and the square root of 9 is 3. So y is equal to, that right there is just a random dot. It's not prime. So y is equal to, this would be 8 radical 2 over 3. Alright, we're going to need this, and we're going to need this. Once you have those two values, substitute them into this equation over here. So x is equal to a 1. So this would be 2 times 1 over 9. Y, we need to substitute this value. And then dy dx stays there. And now the last thing is we need to do the algebra to solve for dy dx. So I'll take this and move it to the other side. It becomes negative 2 ninths. Hold on. Negative 2 ninths. And then this, let's see, this would be 16 radical 2. Multiply, to clear this 3, multiply by 3 on the top and the bottom. These are going to cancel. And then this, I'm just going to leave it as 3 times 16 because I can see that the 16s are going to cancel. Okay, so cancel these. And then cross multiply, so dy dx is equal to, so you multiply, that's going to be negative 6, divide, that's going to be 9 radical 2. And then you could rationalize the denominator if you want to, but that would be dy dx. Okay, then on to something, well, first I want to talk about how you generalize this. So in the last one, the picture was already drawn, and the function was already given. Those are the easy ones. For the more challenging ones that are just word problems, you need to most likely draw a picture yourself. It's probably going to have something to do with geometry, so a rectangle, a rectangular box, a sphere, something like that. You draw a picture. And then you're going to have to come up with the equation yourself much of the time. And usually that comes from geometry or pre-calculus. And then I suggest that you write down the given information. So in this one, here is the information asked for, here's the given information. So I would say write that down. So it could say something, for example, that dy dt is equal to this when dw dt is equal to this when w is equal to 3. So just write that down so you've got your given information. Next, take the derivative. And again, you need to pay attention to the denominator. It's not just going to be dy dx. Most likely it's going to be d some variable over some different variable. It also helps sometimes to keep track of the units. So w is a width, so that's going to be in feet. T is a time, so that's going to be in seconds. And again over here, w is a width, so it's in feet. Next, you substitute the given values and do the algebra. So sometimes what you have to do is go back to the main equation. Like I showed in the last example, you have to go back to the main equation and find any missing information. Then take all of that and substitute it in to your derivative. And finally, solve for the rate, or another word for rate is derivative, that's being asked for. So here's another example. So somehow lightning or whatever, a fire starts and starts expanding out in a circular pattern. So the fire starts right here, and as it spreads, the edge of the fire is a nice perfect circle like I just drew. Now another important thing on these pictures that I haven't mentioned yet is don't just start filling in the numbers. If this radius or if this circle is getting bigger and bigger, we can't just say that it's 15 or we can't just say that it's 30 because it's changing. So what you've got to do is use a variable like r for radius, and r is going to be in good old American feet. Next, we need to come up with an equation. Well, for a circle, there's not a lot of choices. There's area and there's circumference. Well, this one is talking about the burn area. So area, the formula for area is that it's pi r squared. So there's our picture, there's our main equation. Now, what information is given? The radius is growing at 15 feet per hour. So this right here is saying that you've got a derivative, feet per hour. So it's giving you feet per hour. Like I said, the radius is in feet, and this is saying the radius is growing, so that means it's changing. So that means the change of the radius over time is something feet per hour. And in this case, it's 15 feet per hour. So how fast is the fire spreading? Well, we've got dr dt is 15. How fast is so as soon as it says how fast, that's saying find a derivative. For the fire spreading, well, it's spreading out into a bigger and bigger area, so we want to know what's the change of the area with respect to time. And then finally, when time is 2 hours. So there's the picture, the main equation, the given information, and now we're ready to take the derivative. So on this side, you take the derivative of a, so that's going to be the derivative of a with respect to time, which is another way to say how fast is the area changing over time. Since pi is a constant, the derivative over here is going to be easy. You just have to take the derivative of r squared, which is 2r, and then the chain rule says take the derivative of r. So that's going to be the derivative of r with respect to time. Okay, next the question asks for dA dt, so we're solving for this. That means we need a number for this and a number for this. So if we have the dr dt, that's a 15, so we've got a 15 for this, dr dt. Now we need a number for r. Well, if it's growing at 15 feet per hour and it goes for 2 hours, that means that the radius is growing by 15 feet per hour, and it's done that for 2 hours. That means that it's grown by 30 feet. So this information actually means r is equal to 30 feet. Okay, now we have all the numbers we need. Now I just need to substitute them in. So dA dt will be pi times 2, and then what we just got for r, which is 30 feet. And then dr dt, which was given to be 15. And so then multiply all of this out. I'll just use my handy calculator. Pi times 2 times 30 times 15, 2827 0.433. And then the units. Well, area would have to be in square feet. And then time, in this case, is in hours. So that would be how fast the fire is spreading. One other little thing you have to watch out for in our textbook is sometimes the units will not be the same. Sometimes they'll say this in minutes and this in hours. So then you would either have to convert this to minutes, 120 minutes, or you'd have to convert this to hours so that they are both hours or they're both minutes. So there's just little conversion things like that that you have to watch out for every once in a while. Make sure that the units are the same. Here, straightforward, hour and hour. Okay, that was fun. Let's do one more. Number 3. So this is something like a cardboard box. And no matter what, it's got a height of 8 inches. But imagine that this thing is, maybe you've got like AutoCAD or something like that and you're trying to design a box. So you can grab one on your design. You've got this beautiful 3D picture right here in AutoCAD. And no matter what, it has to have a height of 8 inches. Since that's a given, and it's not saying that the height is changing, then you can go ahead and put 8 inches for the height no matter what. But then maybe what you can do in your design is you can grab this corner and you can drag it out to make the thing longer or wider. So this, I'll call it the length L, can change, so that needs to be a variable. And this width can change, so that needs to be a variable. Next up, we need our equation. So this part, yes, I read it, but what I'm really looking for is keywords like this, volume. That will help me come up with the equation. Like I said, a lot of the equations come from geometry. So volume of a box, you just have to multiply the 3 sides. Sometimes I even have students label, here's the main equation, that volume is equal to, and you multiply the 3 sides. Okay, then I'm going to write down the given information. So one of them is that t equals 2 seconds. Another thing is how fast. So as soon as it says how fast, that means a derivative. In other words, find the derivative of the length changing. So in other words, if you change the length over time, that's what the question is asking for. When it's 2 seconds and the volume is changing, in other words, the change of the volume with respect to time is 100 inches cubed per second. And then right here is where I want to double check that all of the units, here's inches and here's inches, so yes, those are the same. This is seconds and this is seconds, so that's the same, and this is inches. Okay, so all of the units match up. We've got inches and seconds everywhere. So I did that and I said, oh, and the width is changing, so that means the change of the width with respect to time is, sorry about that, I didn't see that it went off the page, the change of the width with respect to time is half an inch per second. Okay, now we go back to the main equation and take the derivative. So on this side, you take the derivative of v with respect to time. In other words, how fast is the volume changing over time. And here we're going to need to use the product rule. I'm going to look at it as here's one function and here's the other one, and then use the product rule. So the derivative here is going to be 8, and then I have to take the derivative of w. So that's going to be the derivative of w with respect to time. The product rule says leave the L alone, and then go plus. This time leave 8w alone, and now take the derivative of L. The derivative of L with respect to time. Okay, now that we've got the derivative, we're going to need to plug in these values over here, the given information. So let's see. I'm supposed to find the derivative of L with respect to t. So that's this one. And if I'm supposed to solve for that, then I need a number for this, and a number for this, and a number for this, and a number for this. What have we got? We've got the dv dt is 100, so that's going to be over here 100. How about the dw dt? Oh, that's right here. That's going to be a half. Now we need the L and the W. Well, I don't see where it says what L equals and what W equals, so we may have to do some extra work. Let's see. When t equals 2 seconds, that's information that we haven't used yet. But if this thing is growing by 100 cubic inches every second, and you let that do that for 2 seconds, then we would know after t equals 2 seconds, then the volume would be 200 cubic inches. So basically we're saying multiply this by 2 seconds, let it go for 2 seconds, the seconds are going to cancel out, and then you'd have 200 cubic inches for the volume. And what else? We could then substitute that into this equation right here, and we would have 200 equals 8 times W times L. And I need to be able to solve for both W and L, which means that I left out a little bit of information. So this is the equation that we have from right here. Put a 200 for the volume. Then we've got this right here. And it looks like I left out a little information. So just pretend that that was right here, and it says and L equals 10 feet. Back there at the beginning. Sorry, my bad. Okay, so then we would substitute that in. That L equals 10 feet. And so this is going to be 80, divide both sides by 80. 200 divided by 80 is equal to W. Let's see, that could be reduced. That would be 20 over 8. You could divide by 4 and divide by 4, so that would be 5 over 2, or 2.5. Double check. 200 divided by 8. Whoops. 200 divided by 80, yes, is 2.5. Okay, so 2.5 or 5 halves. So go back to this equation, and for L, that's 10. That's the part that should have been given at the very beginning. I forgot, so I had to add that on. And then we just found that W equals 5 halves. And then we just need to do the algebra. So let's see, this is going to be a 4. This is going to be a 4. So you have 100 equals 40 plus 20 dl dt. So subtract 40 from both sides. And then divide. So it's going to be 60 divided by 20, or 3. And then what would the units be? So this is saying the change of the length, and the length here is given by feet, divided by change of time, and the time in this one is seconds. So in other words, this thing, its length, this length right here, so if you grab this corner and you pulled it out so that the width got bigger, then the length would get bigger, and the length would be getting bigger at 3 feet per second.